Hello, we're back. Trying to understand this algorithm. So one thing, just leaving off last time, that I kind of noticed, I was wondering how I was like, what does this like actually mean to do the mantissa divided by 2 to the 23rd? It's getting kind of hung up on that. What I realized after the fact, though, so I'm pretty sure I realized, is that this expression here is to calculate the numeric value of the IEEE floating point number. So it's like to kind of look at this and say, oh, m divided by 2 to the 23rd. I was kind of trying to think in my mind, oh, is this is this a float? Is this an int? Is this a whatever? I think that's the wrong way to think about it. I think like this, like up here, we're just in abstract math land, where we're just treating the mantissa and we're treating the exponent as like platonic ideal numbers, and like in our minds, and we're just doing math. So that was one thing that I got really hung up on.
Completely different. For no obvious reason at all.
It's just
E by 23 digits. So that's how one could write the bits, but we get the actual number behind the bits with this formula.
Yeah, getting the actual number. It's like a number is an abstract thing.
This should seem familiar to you. Here we have the exponent with 127 subtracted from it, and here we have the mantissa with the extra 1 in front. But now something completely different. For no obvious reason at all, let's take the logarithm of that expression. Since we're doing computer science here, we take the logarithm base 2. We simplify as much as we can. Take out the exponent.
I just want to see. Okay, yeah, I didn't realize we're doing I just didn't even see this, that we're multiplying these two numbers. So this is a number, yeah, we're just multiplying the mantissa times the exponent, like, 5.321 times, the exponent, 10 to the 5th, whatever. Yeah, it's 2 to the whatever. Yeah, so logs, you can just, product of a log is just the sum of the whatever.
But now something completely different. For no obvious reason at all, let's take the logarithm of that expression. Since we're doing computer science here, we take the logarithm base 2. We simplify as much as we can. Take out the exponent, but then we get... We simplify as much as we...
Yeah, okay. You take out the exponent, like, have like log base b of whatever, x to the b, or whatever, to the e. If you're doing log of that, you can just drop the exponent. Just drop the exponent down. This is equal to e times log b of x. And yeah, in this case, it's e minus 127 times log base 2 of 2. Log base 2 of 2 is like, all right, log base 2 of 2 says, okay, so to evaluate this expression, it's saying, all right, what number do you have to raise 2 to get 2? Well, 2 to the 1 is 2. So that's what this number is. It's like 2 to the log base 2 of 2 is equal to 2. That's what this number is defined as. 2 to the x is equal to 2.
And take out the exponent, but then we get stuck. But not so the creators of Quake. Developer Gary Taroli knew a trick to get rid of the logarithm. You see, the trick is an approximation to log of 1 plus x. For small
What are you saying, like, get rid of the logarithm? Like, so we took log base 2 of this whole thing. We would have to take the inverse of that to kind of get the actual value out. Like, if we have like a value x and we take log base 2 of x, in order to get x back, we've got to take, like, I don't know, like the inverse of log base 2 of this expression, and like that would give us x. What is that? How do we undo that? So like log base 2 of x, that's a number y such that 2 to the y is equal to x. So this number is what we have to raise 2 to get x. Kind of confused. Maybe we can do an example. So let's say like 8. So we have, x is equal to 8. If we take log base 2 of 8, that's going to be 3. But we want to get 8 back. So once we have 3, we say, okay, so we just take 2 and raise it to that. So basically, yeah, if we start with x and we take log base 2 of x, then we can take 2 and raise it to that thing, and that'll give us x back. I mean, just to double check it, like we start with 8, take log base 2 of 8, that's 3, and then we take, this is equal to 2 to the 3, which is equal to 8.
You see, the trick is an approximation to log of 1 plus x. You see,
but he's saying just like get rid of the log. He's not saying to like actually undo the log. So I'm kind of confused. Let him cook, see where he's going with it.
Trick is an approximation to log of 1 plus x. For small values of x, log of 1 plus x is approximately equal to x.
Let's see. Is he going to explain that?
If you think about it, this approximation is actually correct for x equals 0 and x equals 1. But we'll add an additional term, mu. This correction term equals 1. But this
let me just verify this. So for small values of x, for small values of x. So let's see what he said. He said, all right, log base 2 of, all right, so let's consider when x is equal to 0. So log base 2 of 1 plus x, that's equal to log base 2 of 1 plus 0 plus the log base 2 of 1 equal to 0. So yeah, we had x equal to 0. We plugged it in here, and we got 0 out exactly. And then he said, all right, when x is equal to 1, we say, so you said when x is equal to 1, and we plug this in and we get it back. It's almost like the identity function. Log base 2 of 1 plus 1 log base 2 of 2 to the 1, so it's equal to 1. So yeah, we plugged in 1 and we got 1 out. So it's saying for small values of x. I think was he saying small positive values? Like, recall that log of negative numbers is undefined, right? Like log base 2 of -1. That's saying like 2 to what power is equal to -1. You can't raise a positive number to any kind of exponent and get a negative number. Like 2 to the 2 is equal to 4, 2 to the 0 is equal to 1, 2 to the -1 is equal to 1/2. 2 to the -1000 is equal to 1 over 2 to the 1000. So you can't have negative values for log. So log is like, so log of 0 is undefined, but log of 1, we say that's 0. So log base 2 of 1 is 0. Log base 2 of 2 is 1. Log base 2 of 4 is 2. So we're growing like exponentially slowly here. 8. It's just a line. Yeah. Oh, wait. But can't have negative values though. Yeah, log base 2 of 0.5. That's going to be -1. Log base 2 of 0.125. That's going to be, okay. It's going to be -1. 0.25 is -2. Half of that is, whoa. Half of that is -4. That's crazy. I never really thought about how quickly this grows downwards. So if we increase exponentially fast, then we'll only get a linear increase here. Yeah, it'll just be a line. Yeah, it'll just be a line. But then if we like decrease exponentially fast here, we decrease exponentially slow to 0. Is 0 exponentially slow? Just not like, if we kind of like blow this up and we're like, all right, this is 1 and like this is 0.5 and this is 0.25 and this is 0.12. What? It's 0.25 divided by 2. 25, 12.5, 0.1125. Point 125. Yeah. 0.125. And then half of that. All right, what? So it's like 12.5. What's 12.5? 0.0625. 0.0625. And then like half of that. Point 0.03125. Oops. Hey. Dang. All right. It's like doing this whole thing. Yeah, let's say like this is 0, this is 1. All right, this is 1. We'll say, all right, so this is 0.5. This is 0.25. Okay, so this is 1. This is 1 over 2. This is 1 over 4. This is 1 over 8. This is 1 over 16. This is 1 over 32. This is 1 over 64. All right, so then this is like log base 2 of 1 is 0. Log base 2 of 1/2 is -1. -1. Log base 2 of this is -2. Log base 2 of this is -3. Log base 2 of this is -4. Log base 2 of this, -5. Yeah, this is very weird. Like, it's very weird. Like on a log scale, it's like on a log scale, this is a straight line. Yeah, it's just really weird to think about because there's like an endpoint here. Like what happens? This is going to get smaller and smaller, but the slope has to it's super weird. I mean, I guess it's almost like you can keep like zooming in on this region here. And like every time you like zoom in further and further and further to 1 over 128, 1 over 256, 1 over 512, 1 over 1024, 1 over 2048. Like, you're just going to keep seeing a line, and you just keep like zooming in and zooming in. It's pretty weird.
Information is actually correct for x equals 0 and x.
Oh yeah. Why is this okay, so that was just about like log being it's for small values of x. Why is that? In general, I'm just trying to think like, all right, in general, this is false because why? All right, let's consider like a big value of x. Like, let's do x is equal to 127. So log base 2 of 1 plus 127 is 128. Log base 2 of 32 is 5, 6 is 64, 7 is 128. So this is 7. So you put 127 in and you get 7 out, and that's like not close at all. And then you do like, I guess this is like x, and we'll say log base 2 of basically 1 plus x. I guess if you put in like 0, then you get out 0. If you put in 1, you get 1. If you put in 2, you get 1. Put in 3, no. 2 is like, it's 3. It's like basically 2. It's like pretty close, but it's like 2 plus just like a small value. You do 3, you get 2. If you do 4, let's do like 1 less. So you do 7, you get 3. You do 15, you get 4. You get 32, you get 5. No, not 32. You do 31. You do 63, you get 6. You do 127, you get 7. 256. So this is like, these are growing like further and further apart as time goes on. We'll say, how about this? It's like this thing is like much greater. This thing is much greater, much greater, much greater, much greater. And then we'll say like this thing's greater, this thing's greater, this thing is equal. Actually, we'll almost say like about 7 is greater, and then 3 is great. 3 is like almost, and 2 is like almost. And then 1 is exactly equal, and then 0 is exactly equal. Oh yeah, okay. So what about within the range here? So 0.5 is like x is equal to 0.5. So then log base 2 of 1 plus 0.5, 1.5. It's going to be somewhere between 0 and 1, but I'm not sure what value it is. I don't have a great intuition for this range here. All right, he's plotting it out and he's saying it's pretty close. This green line is just like x is equal to x. Now I guess it's y is equal to x. And then the blue line is y is equal to log base 2 of 1 plus x.
Equals 1. But we'll add an additional term, mu. This correction term can be chosen freely. Again, with mu equal to 0, this approximation is correct at 0 and 1. But it turns out that setting mu to this number gives the smallest error on average for numbers between 0 and 1.
Okay, that's interesting. I wonder how we could do that. I feel like you'd need an integral.
So going back to our formula, we apply this between 0.
Like, intuitively, what would it be like to actually figure out the actual, like, so if we just choose a value from mu, how do we compute the difference between these two over the range of 0 to 1? Like, if we chose, for example, like mu is equal to, I don't even know, like 0.5, just like a random value, then we could look at, so for the value of x is equal to, let's say mu is equal to like 0.3. And so like, let's look at the value x is equal to 0.5. Then we say, all right, like log base 2 of 1 plus 0.5, basically minus okay, so like we're trying to choose the line of we're not just choosing y is equal to x, we're choosing y is equal to x plus mu. So it's basically x, but it's just a little like offset from it. It's just like shifting it a little up on the y-axis. So we subtract it from 0.5 plus mu is 0.3. And like, I feel like we'd have to take the absolute value. But yeah, if we wanted to do this for the whole thing, I feel like we would sum up all the values in that interval. So it'd basically be like, I guess it'd be like the integral from 0 to 1 of like so for like a chosen value of mu, we say, yeah, let's evaluate log of 1 plus x minus x plus mu dx, I guess. Guess you could do like the absolute value. We just want to find the difference here. Yeah, I don't really know how to evaluate these integrals. This would be an interesting like lark to just go down this to like figure out if we can evaluate this integral. And I just wonder too, do we need the absolute value? Because like here, in this, basically in like this range to this range here, the like this difference is going to be negative. It's going to be negative. And then from here to here, the log term is going to be positive, like on top. And then from here to here, it's going to be negative again. So I don't know if you need to. I don't know if you need an absolute value. I think if you just sum all these up, you just want to get the number that's closest to 0. Like you don't want to minimize. You want to minimize this. Oh, Okay, I guess you do want to minimize like either this or like the absolute value of this whole thing. I feel like that's an easier thing to do. Is that the same thing? Like if you minimize the absolute value thing, if you have a bunch of if you have a bunch of things like x1 minus x2 plus x3 minus x4 plus, and so if you like take the absolute value of each of these things, is this equal to taking the absolute value of is that equal to the absolute value of taking the whole thing? It's an interesting thing to investigate. But just to get it a little closer to what it would to what the optimization would look like is like we want to like basically minimize over mu, basically like the absolute value of this integral 0 to 1 of we'll say that mu star is equal to this thing. Could try different values of mu. Like you could try like kind of shifting this thing like up and down, and just approximating it by just taking these little differences. Like at every point, you compute the difference. Kind of like this. Kind of like that. You just kind of approximate it. Again, somewhere new. Yeah. Anyway, that's cool. I'll write this down. Whatever. We'll just keep going for now.
And 1. So going back to our formula, we apply our trick, as m divided by 2 to the 23 is indeed a value between 0 and 1. We
m divided by 2 to the 23 is a value between 0 and 1. Recall that the mantissa is like 1.011 blah 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 like this, but the mantissa itself, you kind of like tack on the 1. So the mantissa by itself, yeah, you're gonna put like a decimal place. I mean, the mantissa itself should be between 0 and 2. But if you kind of like subtract 1 from this, then You just chop a 1 off of it. Yeah.
A little bit more, and we finally see why we did all those calculations.
Huh.
M plus E
Wait,
times
I missed like the big thing. Why
we apply our trick.
Oh, what the
as m divided by 2 to the 23 is indeed a value between we apply our trick.
So he's basically saying, like, because of the last slide, he's like for small values of x, between x is between 0 and 1, we can substitute this whole thing for just, it's basically equal to x. So it's basically equal to like the thing inside, which is just 1 plus this. So we can just drop the log. Wait. The mantissa is about, this value is going to be between 0 and 1. Hold on, let's see what he says.
As m divided by 2 to the 23 is indeed a value between 0 and 1.
Oh, he said that for small values of x, log of 1 plus x is approximately equal to x. So, okay, cool. So you just... Okay, so you
divided by 2 to the 23 is indeed a value between 0 and 1.
Okay.
We rearrange a little bit more, and we finally see why we did all those calculations.
Whoa.
We rearrange a little bit more, and we finally...
So, okay, all right. So he's just multiplying by 1 there.
Why we did all those calculations.
Okay, how did he do that one?
We rearrange a little bit more, and we finally see...
So he wants to kind of like combine these two terms. I just want to see if I can figure out what he's doing kind of before he does it. So, okay, yeah, we can just combine these two. So it's just like m plus 2 to the 23rd times e over 2 to the 23rd. Is he doing anything else besides that?
Why we did all those calculations?
What? Oh, okay, so it just pulls out the 1 over 2 to the 23 times, yeah, this m plus, yeah, 2 to the 23rd times e. Okay, nothing crazy going on there.
M plus e times 2 to the 23 appears. That's our bit representation. So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants.
What the?
So in some sense, the bit representation of a number is its own logarithm.
What?
Armed with this knowledge, we can finally start with the 3 steps of the fast inverse square root.
What? Okay. Oh man, yo, we're so close. We're so close to getting this. Oh man. Oh, we're so close. We're so close to being able to start. This is the very last thing we need to understand.
And 1. We rearrange a little bit more, and we finally see why we did all those calculations. M plus e times 2 to the 23 appears. That's our bit representation.
Yeah, I mean 2 to the plus The exponent, okay, we shifted over 2 to the 23, and then we just add the mantissa? Is that right? I feel like I need to go back to
We simplify
that thing.
in the number it represents. Now our mantissa is between 1 and 2. Even though 23 bits gave us number 127 subtracted from it, and now only to about 30 is the sign bit. 8 bits we can represent scientific notation, comma after the first 1, and then we add algorithm, subtracted from it, and here we have the mantissa with the extra 1 in front. 23 times e plus
f. Here we go.
r. If we are given two numbers, one being the mantissa and one being the exponent, 23 bits and 8 bits respectively, we can get a bit representation with 2 to the 23 times e plus m, if you think about it. Because multiplying e by 2 to the 23 just shifts e by 23 digits. So that's how one could write the bits.
Okay, so it's not saying that like 2 to the 23 times e plus m like is the number in any sense. It's just like that's how you actually get the bit representation of it. Like that's how we're encoding it. Yeah, I mean, that's just how you do it in binary.
We applied the log. We rearrange a little bit more and we finally see why we did all those calculations. M plus e times 2 to the 23 appears. That's our bit representation. So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants.
Hold on, what do you say?
So let's think about what we just did. We applied the logarithm to our formula and got the...
To our formula. Yeah, the formula was... This was the number. Like, this was the actual number that we were encoding.
Finally see why we did all those calculations. M plus e times 2 to the 23 appears. That's our bit representation.
Okay, so he's pointing this out. Like he's saying that, all right, our bit representation appears right here. Like these two things are the same.
So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants. So in some sense, the bit representation of a number is its own logarithm. Armed with this knowledge, we can...
What the Wait, what?
Finally start with the 3 steps of the fast inverse square root. With the scaled and shifted, we applied representation. M more, and we finally see why we did all those calculations. M plus e times 2 to the 23 appears. That's our bit representation.
Okay, so okay, cool. So like this is the... So this is like the number that we start with. Like this is the long or whatever. And we did... Like this is how we're like encoding the long currently. Like we started with the actual value of that number, like what number it represents, and then we just took the log of it. So we basically, and we got this expression. So basically, if we just start with a long and we multiply it by this number, which is just shifting it down to 23 and adding this number and subtracting that, we can, that's how we compute the log base 2 of that number.
So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants. So in some sense, the bit representation of a number.
We started with our number and then we got the bit representation. We started with the number in like scientific notation or whatever, and then we got the bit representation out of it.
Is its own logarithm. Armed with this knowledge, we can representation of a number scaled and shifted by some constants. So, and got the bit about what we just did. We applied the logarithm to our formula and got the bit representation. Scaled and shifted by some constants. So in some sense, the bit representation of a number is its own logarithm.
Yeah, I guess it's like if you, so I guess what that's saying is like if we have a number, if we just have a long in our hands in this representation, like this thing kind of like was the log. We took the log of the number and got this whole expression. Like this whole expression is the log. Fuck. No.
Armed with this knowledge, we can find the representation of a number is its own logarithm to our formula. So let's think about what we just did. We applied the logarithm to our formula and got the bit representation, just scaled and shifted by some constants.
Okay. So we started, so we had a number and then we took the log and then we kind of like get the same representation thing back like within it, but like a little stuff done to it. So we just need to like, so we just basically just need to like do these little things to the bit representation to take the logs. So is this whole thing just kind of like an easy way to take a log? Is that it?
So in some sense, the bit representation of a number is its own logarithm. Armed with this knowledge, we can finally start with the 3 steps of the.
I don't know if I like him saying that it's basically its own logarithm. I think it's better to say that like its log is like encoded in the bit representation.
Inverse square.
Like it's not like it's equal to the log, or it's not even like it's approximately the log. It's you can just use its representation to compute its log. Hey, what's going on? What's the sound?
The first step is actually not. The first step is actually not complicated. It just looks complicated.
All right, I think this is where I'm gonna kind of like break it. Maybe I'll.
It's memory address
like-
trickery.
Yeah. Okay. I'm pretty fried. All right. Thanks, guys. That was fun. That was pretty cool. Yeah. Next time we'll pick up right here and we'll. Yeah, we'll just do it. We'll keep on going. Kind of thinking like maybe taking some notes. It's kind of like where we left off. It's been this thing happening with my terminal. I don't know what's going on. So just taking some notes. Where we left off is basically given a float, you can use its encoding, its IEEE whatever encoding to compute its log base 2 pretty easily by shifting and adding some constants. I feel like that's the main thing. And now we're going to use that to figure this out, I guess. So, okay, I'll just end it there. Thanks, guys.